We will now solve some challenge problems. A ball is thrown upward from the ground with an initial speed of 25 meters per second. Okay, that's going to be the initial speed, but since it's going upwards, we can call it the velocity and just add a positive. At the same instant, another ball is dropped from a building 15 meters high. So this ball has as its starting height, or its initial y position, 15 meters. When they say dropped, what they mean is dropped from rest. So the initial velocity is 0. There's something else that I forgot to write down in this first sentence. A ball is thrown upward from the ground. Well, if the second ball starts at positive 15 meters up from the ground, how high up is the first ball? Its initial position, initial height, is 0 meters. After how long, that means find the time, will the balls be at the same height? Now the trick here is to realize that if one ball is going up and in the same instant the other starts to fall down, then they will be in the air for the same amount of time t. T is the same for both. Additionally, they will have the same final height. And that's going to be really important information for solving this problem. It's the key to moving forward. The final given that we have is that both are in free fall. So for both, the acceleration due to gravity is negative 9.81. Let's list the givens that we have right now. Here are those givens listed in a chart. When we compare the list of givens to the equations, and it's the same exact set of givens for ball 2, you'll probably realize that the best candidate is the first one. We're using constant acceleration because the objects are in free fall, so they have a constant negative 9.81 meters per second squared of acceleration. So let's write that first equation down, but of course I'll change the x to a y. And I'll write the same equation again here, because these givens are the same. Now, when we look at this equation, there is one small mismatch. We have been given y initial, but the equation uses delta y. So is there any way to combine those two pieces of information? Yes, there is. You may recall that every change is the final value minus the initial. So we can write this as y final minus y initial for both of these objects. And now we are getting somewhere. Because if we isolate y final and do the same here, we can set the two y finals equal to each other because they are the same for both of these balls. Here's what that looks like. And you can see now that I took the original part of the equation, and then I just added y initial to the other side, and it came in right there. So what do we have? Well, we have an equation that we can solve, because in this equation, we know y initial for ball 1, it's 0. We know v initial for ball 1, it's 25. Time is the unknown. We know ag, time is the unknown. On the right side for ball 2, we know y initial, that's 15. Vi is 0. So anything times 0 is all just going to be 0. And again, we know ag, and we seek time. But look at this. That's the same ag, and this is the same time. The two balls are in the air for the same time, so ball 1, ball 2 have the same time. If I subtract 1/2 ag from both sides, ag t squared, then this is going to disappear completely from both sides. And so now I have vi multiplied by t is equal to y initial, and that's it. Vi is 25 on the left side for ball 1. The left side here is all ball 1. And the right side is all ball 2. So what's y initial for ball 2? It's 15. We divide both sides by 25. 3 over 5. This is 0.6 seconds. And I should really be going back and checking my sig figs. The fewest number of sig figs from the givens was 2. So I should make this 0.60. So what was the trick here? The trick was we had to realize that the two objects had certain quantities that were the same y final and the same time. That was one trick. The other trick, we had to realize that we needed to separate the givens for the two objects. That's another key for this question. Separate the given values. On to the next one. There's an 800-meter road trip. A van accelerates uniformly from rest to a cruising speed of 17 meters per second. It maintains this speed for some time before decelerating uniformly to 0 meters per second. Each of the 3 segments, there's a speeding segment, a constant speed, and then slowing, takes the same amount of time. Calculate the total time of the trip. Look at the two tricks that I just showed you. Will either of these work for the next question? Yes, there are 3 segments. Let's break up the givens. Segment 1, segment 2, and segment 3. Now, they told us that the entire trip is 800 meters. So that's going to be this first distance plus the second distance plus the third is 800 meters. We also know that in the first segment, we start from rest, we accelerating, we have a final speed of 17, and that's all we know right now. In segment 2, we know that we have constant speed, and in this case, what is the constant speed? Well, if we think about a motion graph, the velocity increases to 17, then you maintain constant speed, and then you slow down. And I should have drawn this differently because each of those segments lasts for the same time. So if this is like 5 seconds, then this would be 10, and then this would be 15. So what's the constant speed during segment 2? It's whatever final speed you achieved in segment 1, 17 meters per second. That's how fast the car is going when it stops accelerating. So if we have constant speed, there's no need to do VI or VF. We're just going to say the speed V is 17 meters per second. Then in segment 3, we start from that 17 and we slow to a rest. So V initial now is 17. V final is 0. Here we are accelerating as well, slowing down. One final thing we know is that the time T1, the time T2, and the time T3, these are all equal. The other thing we know is that the distance d1, let's use displacement here, the displacement delta x1, the displacement delta x2, and the displacement delta x3, they add to the total, which is 800 meters. That's the total. So how can we solve this problem? The first thing we need to do is acknowledge these conditions, because those 3 things I circled determine which equations we are allowed to use. If you have constant acceleration, then you need one of these equations here. And for segment 1 and segment 3, that's what we need. Which makes the most sense? Well, I've got VI, VF, T, and delta X. I've got some information about those 4 things. Which equation has those 4 things? It's this one. So let's write that equation down for the first segment. All right, the equation is delta x1, because I'm applying this to the first segment, is equal to 1/2 VI plus VF multiplied by T1. And maybe I'll go ahead and plug in VI and VF. VI is 0, VF is 17. So when I work this out, I've now got delta x1 equals, what's half of 17? 8.5 T1. In the second segment, we have constant velocity, so I can't use these equations. Instead, I use this one. So that equation tells me, let's see, let's move this down. The constant velocity of 17 meters per second is equal to displacement, and we're talking about the second displacement that occurs, divided by T2. And in the third segment, we are accelerating again. And if you go through this analysis, you're going to end up with the same exact equation as segment 1. The equation for 3 that we need for segment 3 is this one, because that's the equation with delta x, t, vi, and vf. Let's write that equation down applied to segment 3. Okay, delta x equals 1/2. Vi is, in this case, 17. Vf is 0. And we have the time for the third segment. Notice how I apply the equation to the third segment. And I use these subscripts to differentiate. Delta x1 may not be the same as delta x2. In fact, they're not the same. So the subscripts remind me that I'm talking about different portions or different segments. Okay, when we work out this, we can just simplify a bit. Delta x3 is what's half of 17? That's again 8.5 times t3. Now we are somewhere. Can we plug into this equation? Because this equation has more information we have not yet used. Well, if we plug in for delta x1, what do we get? 8.5 T1. If we plug in for delta x2, what do we get? Cross multiply, and it's 17 times T2. If we plug in for delta x3, it's again going to be, 8.5 T1. Sorry, it's T3, pardon me. And once I get to this step, I realize that I've kind of been doing something unnecessary. There's no need to distinguish time 1 from time 2 from time 3. Those individual increments, the question said, are the same. Each segment has the same time. So we only need a single variable t. We don't need to distinguish if they're all the same. And look at what we have now. You can add these coefficients, combine like terms. What's 8.5 plus 8.5t plus 8.5t is 17t. 17t and 17t is 34. I've lost my units. I've been a little bit careless about units. So this actually here, the unit would be meters per second. I'll leave that as an exercise for you if you want to work out how we know that that's the case. And when I divide both sides by 34, we get our final answer, which is about 24 seconds. Now, I don't even know if that's what they asked for. Calculate the total time. Careful here. What I've just calculated was the individual time t. I said, okay, let's stop using T1, T2, T3. Let's call it all t. But t is the time of just 1/3 of the trip. So my total time would be 24 seconds multiplied by 3. That's going to be, 72. On to the next question. To pass a PE class at university, a student must run 1,600 meters in 12 minutes. After running at a constant speed for 10 minutes, she has 450 meters to go. If her maximum acceleration is 0.15 meters per second squared, can she make it? If not, what acceleration would she need? Okay. This again, let's look back to the original advice. Does any of this help? Look for the same value or equal value, connecting two different objects. That's one trick we've used. And the other is separate the givens if different things are happening. That's the one we're going to need right now for problem 3. We notice that she ran at constant speed for 10 minutes. Let's call that the first segment. Then she accelerates during the second segment. Once we know that, we are off and running. Let's list the givens. This is the total displacement, or the total distance. This is the total time. What else do we know? In the first segment, she runs for a time of 10 minutes, which of course we can convert to 600 seconds. And let's see, that means in the second segment, we're going to come back to that. She still has 450 meters left, so that's what she has to run in the second segment. Delta x2, maybe I should use a 1. How much distance or displacement did she have then in the first segment? Well, the total is 1,600. Subtract off the 450, and we get this. Now her task is to finish in 12 minutes. So if she's already run 10, how much time does she have to spare for the second segment? 2 minutes. We multiply by 60, and this is going to be 120 seconds. We've made great progress already. Here's what we're going to ask. We're going to find the way we'll answer this question, we're going to solve part B first. We will find the acceleration necessary, then we'll compare to what she's capable of to figure out whether she'll make it in the 12 minutes. Now, we know that we need 4 things. We need 3 givens and 1 unknown. So far, I've listed just 2 givens, and I need a third value, a third given. It's either going to be VI or VF. And I need one of those before I can calculate acceleration, because every equation up above has 3 givens and 1 unknown. So what's the 4th given going to be? Well, let's read this one more time. So she has to run, 1,600 meters in 12 minutes. After going at constant speed for 10 minutes, she has more to go, and she starts to accelerate. Wait a second. If we do a velocity graph, which can be really helpful, she's running at a constant speed, and then she accelerates during the final portion. So if her constant speed was known to us, that would be VI for the acceleration for the second segment. Can we find that constant speed? Yes. The left side is the one with constant speed. And the equation for constant speed, or in this case constant velocity, is displacement divided by time. We're applying this to segment 1. And when we perform that calculation, 1150 we said, the time was 600. We get 1.92 roughly. So now we know what speed she starts from, what velocity she starts from. Approximately 1.92. I think it's 1.916 repeating. And at this point, we can now calculate her acceleration. Look at the three givens that we've been provided. These three. Look at the unknown and find the equation with those four quantities. It's the one that doesn't have VF. So there's no VF in my list. Okay, which of the four equations does not have VF? It's not this one. This has VF. It's not this one. That has VF. That has VF. It's the first one that I need. So we write that equation down, and then we're going to plug in the values that we have above. So delta x is 450. VI is 1.91666. And of course, you use the unrounded value when you calculate. Oops. T we know. 120. The acceleration is what we seek. We square the 120. And when we work this out, we get an acceleration of 0.3 meters per second squared. Notice, I'm not using the right number of sig figs. Haha. No, that's not the thing to notice. What I want you to notice is this is the acceleration such that she barely gets there. She barely finishes on time because she finished in exactly 10 minutes plus 2 minutes. So this is the minimum acceleration. Anything faster than this, and she will finish in under 12 minutes. So can she execute this acceleration? Can she achieve this? Yes, she can. So yes, she will finish on time. On to the next question. This one is really a doozy. If you thought the others were hard, wait till you see this. Okay, take a moment. Here's what I challenge you to do. Read the question, pause the video, figure out which tricks that we've used can be applied to this problem. Okay, hopefully you've had a chance to look at this and figure out which tricks to apply. Here they are, both of them. We have here a car whose givens we must separate from the bicyclist. I'll just say bike. Moreover, for each object, there is a first segment where they accelerate, and then a second segment where they have constant speed. So maybe I'm going to need some more space. Let me move this over. And that's what makes this problem so hard. The bike also has a first segment and a second segment. So in a way, there are four problems, well, four equations at least, coming into play all in one question. So take a moment now, pause the video again. Given this, can you read the problem once more and identify the givens in the correct spots? Okay, here are the givens. Let's see if you got it right. For the car, it starts from rest, so VI is 0 miles per hour. VF is 50. The acceleration is 9 miles per hour every second. That's how much the velocity increases every 1 second, is by 9 miles per hour. In the second portion, just for the car, it reaches this speed and then moves at a constant speed. So the constant speed during the second segment is just what it achieves after accelerating, 50 miles per hour. Okay, now see if you can pause the video and fill out the givens for the bike. Here are those givens. There is yet another trick that we have to use. We know that at the and so the question, let's read the question. The question says, how long is the bicycle ahead of the car? In other words, we are looking for the time t. Now, in this question, we have to visualize the picture. The bike gets an early head start, and the car eventually catches up. So in the very first moment, here's the car, here's the bike. I can't really draw a bike. And then a little bit later, here's the car, here's the bike. And then a little bit later, here's the car, and here's the bike. And then at some point, the car starts to catch up. So after a little bit more time, this is going to be really inaccurately drawn, but this is sort of what's happening. Here's a little time later. Here's a little more time later. You can see the car is closing in, and eventually the car has caught up, and the bike and the car are like passing each other. So the question is, are there any quantities that are the same for the two vehicles? Well, yeah, definitely. The total displacement is the same. That means, remember, if we add the displacement in the first segment and the second, they will add to be the same for both vehicles. So let's add displacement to our list. There's a first displacement for each object. There is a second displacement for each object. And if we knew delta x1 and delta x2, we could add them. For the car, the sum is equal to that of the bike. Okay, is there any other quantity that's the same? The total time also is the same. Because they start at the same time and they meet back up at the same time. So the time it takes is also constant, or rather is the same for both vehicles. So T1 plus T2 for the car would equal T1 plus T2 for the bike. Should I add a C here for car? This is getting a little complicated, and a B here for bike. This feels like too much. What I like to do instead is I just remember that the left side is car, the right side is bike. But really, these delta x1, this is not the same as this. They're different. Okay, let's continue on. Now, if you're like me, this is a lot of information and it's hard to know how to proceed. So watch what I'm going to do. I'm going to find anything that I can. When I look at this first portion where there's acceleration, I say, hey, hang on, I have 3 givens. So I could go find delta x1, and I can also find the time, t1, that I hadn't even listed. That's going to be possible over here as well. I can find the first displacement for the bike and the first time for the bike. Which equation has these 4 things? Look up at your list. It's this one. Vf squared equals Vi squared plus 2a delta x. When you plug in Vf is 50, square that, you get 2500. Vi is 0. 2 times a is 2 times 9. It's 18. This is the first displacement of the car. When you solve for displacement of the car, what do we get? It comes to 138.8 repeating miles. What else can we find? We can find the time. Pick an equation. The one that I'll use is acceleration is Vf minus Vi over t. If you cross multiply both sides by t, you get this. To finish isolating time, we have to divide both sides by acceleration. And we ended up just flipping these two. So when we solve for the time t1 of the car, final speed was 50 miles per hour, the initial was 0, and the acceleration was 9. So 50 over 9, that's going to be 5.5 repeating. Take a moment, perform the same calculations for the bike. Find the bike's delta x1, its first displacement, find its first time. Okay, when you do those calculations for the bike's first displacement comes to 15.38 miles, and its first time comes to 1.538 seconds. Where does this leave us? Well, we have some really good information about delta x1 and delta x2. We know those values. Can we find an expression for delta x2 for each of the objects? We know their first displacements. Can we get their seconds? All right, let's see. If we look back to the original segment 2, in this second segment, they have some time t2. Each of them has a second segment with a second time. Because they had constant speed, the only equation that we can use, or constant velocity, the only equation is velocity equals displacement over time. And if we cross multiply, we now have an expression for delta x2. Let's plug that in to this equation right here and see what happens. Okay, delta x1, that's going to be what we calculated before. Let me move this down. Delta x1 is 138.8 miles. Delta x2, we cross-multiplied up above. And what did we get? 50 times t2. And of course, t2 here is for the bike, the car. The other side, the right side, is for the bike. And we keep going. On the right, so we're done with the car. Now time to turn our attention to the bike and its values. Delta x1 for the bike was 15.38. And delta x2 for the bike was, we cross multiply, 20 times t2. And now we have to remember that this t2 is for the car, this one is for the bike. So how do we move forward at this point? We realize that if you start with the total time and you subtract away t1, you are left with the time for the second segment. Why is this such a handy little trick? Why is it nice to use this value we calculated? Well, for one, we know something. It's something we know. That's better than knowing nothing. But additionally, these are the same for the two vehicles. That's one of the things we said at the beginning. So now we have 138.8 plus 50 times, let me just call it t for the t total. 15.38 on the right side, plus 20 times, I'm replacing t2, I'm substituting in, with t total, right? I'm just calling that t now, minus 1.538. And this is one equation with one unknown. That's something we can solve. You would distribute, and I'm jumping to the end, but when you work all of this out, you get about 4.1 seconds as the final answer. Okay, wow, what a problem. Let's move on to one that is actually much easier. A stuntman or woman sitting on a tree limb which wishes to drop vertically onto a horse galloping under the tree. The constant speed of the horse is 10 meters per second, and the man or woman is initially 3 meters above the saddle. How long is he in the air? What must the horizontal distance between the saddle and the limb be when he makes his move, or she? So here's the picture. Here's the horsey. I've never drawn a horsey. This is the first time I've ever tried. Pretty close, right? Yeah, perfect. Great horse. The horse is running this way. And here's the woman. That's a tree. Apparently my inability to draw horses has now transferred over, and she's hanging, waiting to drop. The horse is traveling at a constant velocity of 10 meters per second. She is how high above the saddle? 3 meters. Now we know that when she releases, she will release from rest. Her VI will be 0. She will be in free fall. She doesn't feel substantial air resistance. The displacement that she undergoes will be negative because she travels down. And we need to know, how long is she in the air? Finally, an easy question. So how do we solve? You look for the equation with those 4 things. All right then, which equation? It's going to be this one. See if you can plug in the values and solve. Here's what I got. Notice that VI was 0. 0 multiplied by time, it doesn't matter what time is, but 0 multiplied by anything is 0. Notice how I use delta y, because she is moving vertically, not left or right. Now for part B, that's part A, done. What horizontal distance between the saddle and limb must there be? Well, from the moment that she falls, she has 3 seconds to drop. In the same 3 seconds, 3 seconds, where did I get 3? In the same 0.78 seconds, the horse will be traveling forward at 10 meters every second. So how far will the horse travel forward in this amount of time? How much distance must there be between them to line it up perfectly? Well, the horse has a constant speed, so we use the constant velocity equation for the horse. The horse's velocity is 10. The displacement is what we want to know, how much horizontal displacement between them. And the time that the horse is going to be running before she lands on the horse's back is 0.782. We cross multiply, and we can see pretty clearly this will be about 0.78 meters. And that is our answer.